Hi everybody, Dr. Redsek with you here. This is our intro video on section 14.6 about tangent planes. Let's get started. So this is 14.6 and is all about tangent planes. Now this is a two-day discussion, so our goal today is to make sure that we know how to write down the tangent plane when we're given a surface, and then we'll have time in the next video and over the next couple days of class to talk about what this might be good for and talk about various approaches to the same computation. For now, though, we just want to keep it straightforward and draw our classic picture. So the classic picture is you got a surface, some kind of a flying carpet. This is, let's say, z equals f of xy. And it's floating in 3D space as usual, so maybe the axes are like this. There's z, and then maybe here's y, and here's x. It's our classic drawing, and we're wondering about building a tangent plane to this surface, say at this point here. So that point definitely corresponds to some input down in the xy plane. So let's call that input x naught comma y naught flat in the xy plane. And we want to think about how to build the tangent plane there by trying to come up with a couple of tangent vectors in very specific certain directions at that point on the surface. So what we have in mind is to think about the path through that point in the pure x direction, and to think about the path through that point in the pure y direction. So say those are the two paths. We can then compute the slopes that hikers on those paths would encounter as they pass through that point and use them to build tangent vectors, one in the pure x direction, one in the pure y. So here's the one in the pure x. So that's a tangent vector to that path on the surface. And then here's one in the pure y direction. That's a tangent vector to the red path on that surface. Now, if we cross those two vectors together, we'll have a vector perpendicular to the surface. And that's exactly what we need to play the role of our normal vector to our hoped for tangent plane. So it all comes down to writing down those two vectors. So let's see if we can figure out what those vectors are. So there's this vector here, the green one, and there's this vector here, the red one. Let's talk about green first. The green vector, well, for sure, the coordinate of that vector in the y direction is 0. Remember, that vector points pure x. So there is no y. Likewise, for the red vector, that vector points pure y. So there is no x. So that's a start on identifying those vectors. Now, the way to get the other two components of each of those vectors is to think about the slope. So on that green path, the slope is partial derivative df dx. That means if you go 1 unit in the x direction, then the z changes by df dx. So let's have 1 as our x component and df dx at that point. So I'm suppressing all that notation. That component of that vector is an actual number, like say you found out the slope on the green path through that point was 4, then that third component of the green vector would be a 4. Likewise, if we go 1 unit in the y direction for the red, then our z will be whatever the slope was in the y direction at that point. Crossing these vectors, we obtain a normal vector n. Normal meaning perpendicular, in this case, perpendicular to the surface. You guys are going to cross those two vectors. So 1, 0, df dx, cross 0, 1, df dy. So you got to reach into the Math 143 Calc 3 toolkit there and cross those two vectors. If you do cross them, go off to the side. You guys can check this on your own. You get this. It's the vector negative df dx, comma, negative df dy, comma, 1. On our picture, that vector is here in blue. Where it makes a 90-degree angle with both the red and the green, and so serves as the perfect normal vector for the tangent plane we're trying to build. All right, so at this point, think what we have. Think about the ingredients we have. We have a point on the plane, so that would be x naught, comma, y naught, comma, f of x naught, y naught. That's this point here. We also now have a normal vector, and you guys know from 13.5, Calc 3, last quarter. Once you know a point on your plane, the tangent point, and a normal vector, the blue vector n, you know the equation of the plane. So the tangent plane that's the dog. Shh. That's the dog. Sorry, everybody. Hey! Shh. No. So the tangent plane at the point x naught, y naught, f of x naught, y naught is none other than, well, its first coordinate of normal vector times x minus x naught plus second coordinate, note that it's negative, of normal vector y minus y naught plus third coordinate of normal vector, just a 1, z minus f of x naught, y naught. And that you recognize as a giant dot product. You got your normal vector, and you're dotting it with vectors that are in the tangent plane. So a point x, y, z belongs to this plane precisely if, when you do that dot product, it comes out 0. Because every vector in the plane is perpendicular to that normal vector. And that's it. That's how you figure out the equation of the tangent plane to the surface z equals f of xy at the point x naught, y naught in the domain. You can see that tangent plane up here on our drawing in orange. It's the plane spanned by the green and red vectors. So that tangent plane looks something like this. It's what you can make out of the green and red vectors. So that's the tangent plane, and this is its equation. Okay, so all we really want to accomplish beyond that today is let's make sure we can do one example. So let's get a clean sheet and let's do a concrete example just to make sure we can put all this into practice. Because really, you're going to memorize that box. You're not going to cross vectors each time. You're not going to go and rebuild the green vector and the red vector every time. You're just going to know, oh yeah, when I have to build a tangent plane, this is what I do. So here's an example. Let's say you got the surface z equals x squared minus xy minus y squared. And we want the tangent plane at the point 1, 1, minus 1 on the surface. Okay, well, the solution, if you look back at our formulation of the tangent plane to a surface in that black box, I guess we need a few ingredients. We need the x partial at the point in question, and we need the y partial at the point in question. And that's all we need. And these things are straightforward at this point in chapter 14. So let's compute. If you take the partial with respect to x, you get 2x minus y. If you take the partial with respect to y, you get negative x minus 2y. If you consider what that comes out to at the tangent point, so when x and y are both 1, you get df dx at 1, 1 equals 1. And likewise, if you evaluate df dy at 1, 1, you get negative 3. And so we're done. We're done. We're right there. Look how short this problem is. So the plane is, it's negative x partial times x minus known x. Take away y partial, and minus minus is plus 3 times y minus known y, plus 1 times z minus known z. Known z is negative 1 and minus minus is plus, so z plus 1. And all that equals 0. That's it. That's our answer. So the book might display their answers like that, or they might opt to multiply everything out. So you could, if you felt like it, write this as negative x plus 3y plus z equals, and then let's get the constants all on the other side. So you're going to pick up a positive 1 and a negative 3, so that's negative 2, and a positive 1, so that's negative 1, and then swing that to the other side. That's another way that we might opt to write that tangent plane. But really, all this amounts to is picking up all the right ingredients from the information given in the problem and just exploiting that box, which tells us the equation of the tangent plane to the surface z equals f of xy at the point x naught, y naught, f of x naught, y naught. Okay, go practice some suggested problems. You just have a very small handful of suggested problems for day 1 of 14.6. And make sure those are dialed in, and we'll talk about it in class. And we'll try to get a little more mileage out of this tangent plane idea over the next day or two. Okay, see you next time. Bye.